So dear students, welcome to another lecture of digital control systems. So this lecture is dedicated to the Z transforms. So in this lecture we will study about Z transform, and we will understand is its basic knowledge, right? So what is a Z transform? Okay. So in continuous time systems, if you have seen, uh, we have when we have to do the frequency domain analysis of a continuous time system. So for that we have one tool which we call as um, Laplace transform, right? So a Laplace transform is basically used to do the frequency analysis of any continuous time system. So similar to uh, Laplace transform, we have Z transform for the discrete time systems, right? So Z transform does the same thing for discrete time systems, which a Laplace transform does for continuous time systems. So now, as I have already mentioned, that Laplace transform is a tool which is used to analyze the analog systems or signals, which we also call as the continuous time signals or continuous time systems in frequency domain. Okay, so generally the signal or system is in time domain. We convert that signal or system from time domain to frequency domain, and for that Laplace transform is used. Now all the continuous time systems or analog systems or signals are actually represented with the differential equations. So these differential equations are transformed to the complex S plane by using the Laplace transform, so that we can get the frequency analysis of the given system, which is represented by the differential equations. And then we convert, after doing the analysis of the continuous time system in S plane, we convert that that Laplace transform back into the time domain, right? By using the inverse Laplace transform tool. So it is similar, the Z transform is actually similar to the Laplace transform, right? However, in discrete time systems, because discrete time systems are the systems or signals which are available at some specific point of time only. So discrete time signals or systems are generally represented through the difference equations. So to have the frequency domain analysis of such systems, we do not use a Laplace transform. Instead, we have another tool which we call as Z transform. So this is used to have the same analysis for discrete time systems as Laplace does for the analog systems, right? So for any given sequence, which is a discrete time signal or discrete time sequence, so the Z transform of this sequence is generally given by the formula Z of xn. So here Z represents the Z transform of xn. So it is xz, right? So it is given by summation from n is equal to minus infinity to infinity xn z raised to the power minus n. So this is what we call as a double-sided Z transform. This is a double-sided Z transform. That means in this we will have the uh, signals available on both sides of the vertical axis, right? So this is a double sided, that is its limit is extending from minus infinity to infinity. Now, uh, here z is basically a complex variable. It is the variable represent. It is a variable which is related to the z plane. Like in continuous time systems or signals, or you can say the analog signals, we have uh, the uh, S operator or Laplace operator, S operator or Laplace operator. So similarly, we have a Z operator, right, in Z transform. Uh, if we have to get the one-sided Z transform of any sequence xn, so xn for one-sided sequence, xn could be causal sequence or it could be non-causal or anti-causal sequence. So if it is a causal sequence, then the Z transform of xn, which is a causal sequence, can be written as this equation, equation number 2. So it is xz is equal to summation from minus sorry, n is equal to 0 to infinity. So here all the sequence are on the on uh, this particular side of the vertical axis, right? So this is a one-sided sequence, a one-sided z transform of the given causal sequence. Now, if we take the Z transform of a causal sequence, so the Z transform of causal sequence Xn will give us the equation in terms of Z, which will have negative powers. Okay, so we will do some numerical also on this, and then we will understand how it is true. Then generally all the sequence which are available to us, all the signals or systems which are available to us are actually causal sequence or signals or systems, right? So we have to assume them as causal only. Otherwise, if it is not causal sequence, then it would be stated, it would be described or defined or specified. If it is specified, then we have to take it accordingly. Otherwise, we can assume it as a causal sequence. So all the causal sequence will be available for the past samples, right? We do not have the future samples for the causal sequence. Similarly, if xn is a non-causal sequence or anti-causal sequence, so the z transform of such sequence will be given by this equation number 3. So here xz is equal to summation where the limits are extending from minus infinity to minus n. So all the signals are available for the negative, right, samples, right? So where the n is negative, right? So it is anti-causal or non-causal sequence. Now, uh, it is also one-sided. However, when we take the z transform of such sequence, which is anti-causal or non-causal, so such sequence will give us the positive powers of z when the z transform is taken for such sequence. Now, uh, the next thing we need to understand is that this was all about the z transform, whether the z transform is one sided or it is double sided. Okay, so if it is a double sided, then both type of sequences are involved, whether it is causal or non causal, right? um, okay, and the z transform of such double sided sequence will give us the positive as well as negative powers of z. However, if it is a one-sided sequence, so it could be either causal or non-causal. So it cannot be both. So in case of causal, we will get the negative powers of z when the z transform is taken or evaluated. And if it is anti-causal, then we will get the positive powers of the z in the z transform of the given sequence. Now, the next thing we need to understand is that how will we map the given continuous time system into a discrete time system? So generally we have the analog systems or analog signals available to us. We need to convert the analog signals into the discrete. So to convert the analog signal into discrete, we need to follow certain steps. That is, we need to sample the analog signal, we need to quantize it, then we get the discrete, a pure discrete signal or sequence. Now, if we have a continuous time system which we do not want to sample and then quantize, if we directly want to map this particular sequence into the z plane, because analog sequence is available in S plane. So that is, the frequency domain analysis of analog sequence is done in S plane. However, the frequency domain analysis of discrete time system is done in Z plane, right? So if we want to map an analog system which is in S plane directly to Z plane for this to get the discrete equivalent of that analog, so we need to apply some uh, method to get that. Okay, so for this, let us consider one sequence which is xk, and which can be represented by the train of impulses. So train of impulses means we have the impulse sequence which are generally scaled and delayed impulse, right? Scaled and delayed impulse sequences. Okay, so let us say that this impulse, and we will call it as impulse modulated signal. So x star t is that impulse modulated signal. Now, what do we mean by impulse modulated? That actually it is an impulse signal, an impulse sequence. However, we have modulated this impulse sequence with the values of each sample. That is the magnitude of each sample. Okay. So as you can see, x star t is written as x0 delta t. So what is this delta t? This is basically the unit impulse sequence, unit impulse function, sorry, unit impulse function. So this is a unit impulse function, whereas x0 is basically the magnitude of the first sample, or you can say the zero sample, right? The first available sample. It could be a zero sample or first sample, that is a different thing. Then we have this x1. So this x1 is the amplitude of the next sample. Okay, this could be some value which could be 1, which could be 0, which could be any value, right? Then we have delta t minus t. So this is a delayed impulse function. So it is delayed by t value, right? It is delayed by this value. So similarly we have all this. So we call this as the train of impulses, or we call it as impulse modulated signal. So this particular x star t can be represented with a single equation, which is given by equation number 5. So here, as you can see, k is from 0 to infinity xk delta t minus kt. So this is how we can represent the given sequence. Uh, Now, if we take the Laplace transform of this x star t and the Laplace transform, because this x star t is actually representing a discrete signal, but it is continuous with respect to time, with respect to the amplitude, basically. Now we will take the amplitude values as it is. So here, because we have sampled the total time t available for the signal, and we have divided this t into some k samples, each of which is equal to t duration, right? We have the total duration is t, and this t is divided into k samples, and the time period of each sample, or time period between the two successive samples, is capital T, which is fixed. So we can represent any xk as x star t. So x star t is also representing the same thing which xk is representing, right? However, we are considering it, instead of taking kt, we are taking it as t. Okay, so if we take the Laplace transform of this given signal, which is x star s, so it will be given by standard Laplace equation. where xat represents the analog signal, right? So now delta t represents the impulse function, and this is the standard Laplace equation. So delta t, which is this impulse function, is given by this one. So delta t, this is an impulse function which is given by this one. For k will be from 0 to infinity. So we have, this is actually representing the train of impulses, right? Train of impulses. So we will get the delta t like this. So we will have these many samples, common unit samples, one which will have the magnitude 1, so which are placed at some time period t from each other, right? So this is how. Now if we replace this delta t in this equation with this particular equation, we will get a new equation number 6. Now if we put t is equal to kt in this particular equation, so we will get, because now we have used the actual sampled time period, where t represents the total time duration for the available signal, and k represent the number of samples in which that time's duration is divided, and capital D represents the time period of each sample. Okay, that means if you have a analog signal like this, so if you divide this signal into, let us say, k samples, 1 2 3 4, like k samples, so the difference between each sample is t. So you have total samples for this duration t is k, so total time t will be equal to k into t, right? So we have replaced t is equal to kt in equation number 6. So now when we do so, we will get this equation here, right? Because in this, if we put delta kt minus kt, so it is delta 0. So delta 0 is 1, right? Delta 0 is 1. Okay. So then we will have this equation number 7 with us now, right? Now, if you see this equation number 7, in this we have a term which is e raised to the power minus ts, or e raised to the power ts, right? So if we put e raised to the power ts with z and we rearrange this equation, so on rearranging this equation, we will get the value of s here. So s is equal to 1 by t natural log of z. So put we can replace the s operator in any continuous time transfer function which is available to us with this equation, so that we can easily get the z transform of the given continuous time system. Directly we will get. So this is how we will map. So what I mean to say, that if you want to map a system which is defined or described in S plane, and you want to map such system into Z plane, so for that what you need to do, you need to replace S with this particular equation. Okay. Now Z is equal to e raised to the power t s, so where S is actually given by sigma plus j omega, right? Because S plane has two axes, one is real axis, one is j omega axis. This is what S plane has. So now we have replaced S with S equal to sigma plus j omega, and we have got this equation. So here this is a constant term, so it is given by r, and this is an imaginary term, so it is given e raised to power minus j, and this is omega again, right? So now this equation can be represented with a unit circle here, right? As you can see, it is represented with a unit circle, wherein this r is equal to 1. So if the radius is, this is r actually, so if r is 1, so we call it as unit circle. So this is the identification of the z plane, because in s plane what we have, we have virtual axis, imaginary axis g omega, we have a real axis sigma. So this is what S plane is. But Z plane is not represented like this. Z plane is generally represented by a circle with radius r, right? So if r is equal to 1, so we will call this circle as a unit circle, and it plays a very important role in the analysis, stability analysis of discrete time system, right? So this is used for the stability analysis of discrete time systems, right? So this plays a very important role. Now we have S is equal to 1 by Z natural log of Z, 1 by T, sorry, natural log of Z. Now what we will do, we will replace this equation in equation number 7. Now equation number 7 is given here. So what we will do, we will replace this with uh, Z, this one, and then we will replace S with S operator with this equation, right? So let us see what happens. Now when we substitute Z is equal to e raised to the power ts and S is equal to this in equation number 7, so we have this equation with us. So this is uh, we are mapping, actually this is what mapping is, right? So this is what mapping is. We have mapped the continuous, because equation number 7 is in S plane. S, we have S operator here, Laplace operator. Okay, so what we have done, we have replaced S with this equation. So we have got Z transform directly. And if we see, we have got this particular equation here, because e raised to the power minus stk. So what we have done, we have replaced e raised to the power st with z. So if we put here, so we have e z minus k, right? So this is what we have here. If you see, okay, z raised to the power minus k. Now, if this t, capital T is fixed, this is fixed or constant, because we have uniform sampling. Because we have uniform sampling, so due to that this t is fixed. Now when this t is fixed, we can simply replace kt with k. So this is what we have done here. So we have replaced kt with k, and hence we have got this particular equation. Now if you see this equation directly represents, or it is directly equivalent to the equation number 2. So you can check the equation number 2 here, right? So in equation number 2, we have z of x n is equal to summation n is equal to 0 to infinity x n z minus n, right? But here what we have k instead of n. So this equation is directly similar to equation number 2, and it represents the one-sided Z transform of the given discrete time, uh, you know, or you can say an impulse modulated signal, x star t. Okay, so we have derived all this from x star t only, right? So this equation number 12 can also be written as equation number 13. So we have xz, which is nothing but Z transform of a sequence xk. So xk is equal to xkt for fixed t, and xt can also be written as x star t. So we can write it as this one. Xkt can be written as x star t, and x star t is the impulse modulated sequence, right? So now this is the Z transform. This is how we map actually any system which is in continuous time, which is represented or described by the Laplace transform. So we can map such system directly into the discrete time by replacing S with this particular equation, right? Now next we have how to find out the transfer function in Z plane. So as we know that any discrete time system is represented by a difference equation. So we have a linear difference equation, for example here, where we have yk and rk's. Rk's are the inputs, yk is the output, and a1, a2, a n are some coefficients which are real coefficients, and they are generally constant. Similarly, b0, bi, bm, all these are the coefficients, right? Now, if we apply Z transform here and we rearrange this equation, so we will get xz, which is nothing but yz by rz. So it would be given by this particular equation, right? So where m is always less than n, where m is the m represents the we have number of zeros basically, right? M represents the number of zeros, right? And n represents the number of poles. So number of zeros shall always be less than number of poles. Ideally we can have number of zeros equal to number of poles. However, we cannot have m greater than, we cannot have m greater than, sorry, we cannot have this like greater than n. We cannot have more zeros than poles in any given transfer function. So these b naught, b1, bm, all these represent the zeros of the given transfer function, this one. And similarly a1, a2, a3, all ai's, they represent the poles of the, because they are in denominator. Pole is always in denominator, zeros are always in numerator, right? So this is how we can get the transfer function also. So this is it for today's lecture, guys, and thank you so much.